Okay, so the next speaker is Sanna Soomro from the University of London, and he will talk about a class of new asymmetric non-convex Huber loss functions and its derived scale mixture of normal distribution. Please, the stage is yours.
Thank you so much. Yeah, thank you for the introduction. I'm from Brunel, University in London. I'm a final year PhD student in statistics, and this is one of my main projects which I'm currently drafting into a paper for publication. Just before I start this presentation, I just want to give a quick note that I'm deafblind, and so I'm hearing and visually impaired, just what you want to know. Okay, so here's the outline. So I'll first talk about relate words. Here are some existing loss functions which some of you may recognize in statistics. For example, the first loss function is square loss, which is one of the most popular loss functions in statistics and machine learning. This loss function can easily transform into normal distribution PDF, which is given up here, and it can be expressed as scale mixture of normal, or SMN for short, which can be expressed as mu plus sigma times standard normal, where mu is mean and sigma is standard error. And then we have the second loss function is absolute loss function, and this can be transformed into Laplace distribution, and it can be expressed as scale mixture of normal, which is given in reference, but it has a scale mixture of normal distribution with exponential density. And then third loss function is quantile loss function, or some people call it as check loss function. This is very popular for some application that does not work well for symmetric data set, and this one is very good for asymmetric data set. So this quantile loss function can be transformed into a PDL, which is given right here. It's called asymmetric Laplace distribution with an additional parameter tau. Tau is the quantile level between 0 and 1, which control the quantile level. If we set tau equals 0.5, it will be reduced to symmetric Laplace distribution, which is in its second row. So the second row is the special case of the third loss function, and it can also be expressed as scale mixture of normal with exponential distribution, just like in the second one, but with an additional parameter tau. I will discuss the other two loss functions later on in more detail. Okay, so here's some just a bit more in literature before I introduce the new loss function. So typically for symmetry problem, for symmetry problem, the either mean a square loss or Huber loss function of very popular choice, but usually Huber is more popular because it's robust to outliers. However, usually in real life problem, they're not symmetry, and we need some kind of different loss function that is not symmetry. And we have another problem is outliers problem. Outliers usually in works they first pre-process before modeling. They remove outliers, but we may not need to do it. We can fit a model where it can be robust to outliers. And yes, so for outliers, there are some words like we can use symmetry. Symmetric heavy tail distribution can be used because heavy tail distribution takes account of the extreme values which are outliers. But because the distribution can be skewed because of outliers, that sometimes happens. So that another work develop a skew heavy tail distribution for this kind of problem. And also, you can use scale mixture of normal distribution with this kind of problem because scale mixture of normal can take account of heavy tail. Okay, so therefore, I want to present a new loss function called asymmetric Nonconvex Huber loss function, and I'm going to present a probability density function and then derive a scale mixture of normal expression, and then we'll analyze. Before analyze, I'm going to develop methods, Bayesian and maximum likelihood estimation methods, and then we analyze how good this loss function can perform based on stimulation, and then apply it to financial stock markets. Okay, so yes, let's just remember earlier these last two loss functions. Now I'm going to talk about more in detail. These two loss functions are called generalized Huber loss function, which are Nonconvex Huber and soft Huber, which I present these two loss functions. So you can see the first one has square term, which is soft Huber, and the second loss function has absolute value, which is Nonconvex Huber. We have two initial parameters, zeta and beta, which are hyperparameters, and they need to be positive to make this loss function more valid. So what's special about these two loss functions? So the first loss function, soft Huber, can bridge between absolute loss function and square loss function. And the second loss function can bridge between square root loss and absolute loss function. So that's kind of property they have. Okay, and based on this loss function, the order, let me go back to the list. This order derives the probability density function I'm giving here. With it over there. is based on logarithmic scoring rule. Then based on PDF, you can derive a scale mixture normal, which is given by here. So the first one, Huber, has scale mixture normal with the following generalized inverse Gaussian with hyperparameters. And the second, Nonconvex Huber, has scale mixture normal with generalized inverse Gaussian and W following exponential distribution. Okay, so now I'm going to present the new loss function, which is the asymmetric version of Nonconvex Huber loss function. So I'm going to introduce this skewness parameter tau, which can also act as quantile level between 0 and 1. So, and that's only one additional parameter here. And then I transform this loss function into PDF, which is given by here. You have normalizing constant multiplied by exponential to parallel of a negative loss. And I can derive a scale mixture of normal expression, which is given by here, with a generalized inverse Gaussian and exponential, but now I have tau parameter in here. If you observe, if I set tau equals 0.5, it will reduce to this second scale mixture up here. So Nonconvex Huber is a special case of my loss function. Okay, so just want to visualize what's happening in my loss function. So in each plot, I have 5 curves which represent 5 different values of tau, and each plot gives different values of beta and zeta hyperparameters. Okay, so if we look at the first plot up here, so if we look at black curve, for tau equals 0.5 median, for symmetric case, if you can see, it's kind of like gives similar shape as square root shape for small value of beta and zeta. As we increase values of hyperparameters, beta and zeta, you can see the shape becoming a straight line, which is like absolute loss function. So I would say that this loss function is actually bridge between square root of quantile loss function and quantile loss function. Okay, so now work parameter estimation method. If you remember, I have the PDF. The PDF, and now I'm going to use this scale mixture normal expression. I'm going to develop the Bayesian method. So I have this hierarchical model based on scale mixture normal expression. I have the response variable yt following normal distribution with other parameter where we have W following exponential distribution, and sigma following generalized inverse Gaussian. And of course, we have to assign a higher mean for mu, standard normal distribution, and also the important assumption we have to make is that both sigma and W have to be independent of each other over t equals 1 to capital N, where N is sample size. And I define what is kappa 1 and kappa 2 because they contain the tau parameter or skewness parameter. Okay, so based on hierarchical model, I can easily derive a new posterior, I can easily derive a closed form posterior distribution for sigma, W, and mu. So I have derived a closed form where W and sigma following generalized inverse Gaussian and mu following normal distribution. However, we don't have a closed form for tau, so I'm going to use this method, random walk metabolus algorithm for tau. Okay, so this is it for Bayesian method. Now the next method is maximum likelihood estimation method. Okay, so let's, as usual, given data, we have this simple linear regression model, yt equals mu plus epsilon, where epsilon follow asymmetric Nonconvex distribution. Asymmetric Nonconvex Huber distribution, and just figure about scale mixture of normal expression using PDF to write this likelihood function, which is given by here. And as we can see, it's a bit complicated. So I'm going to use the non-derivative based optimizer method to estimate mu and tau.
Sorry, Sanna.
Yes.
8 minutes left.
Sorry?
8 minutes left, roughly.
Sorry?
8 minutes left till the end of
Okay. Yeah.
okay.
Yeah. So I'm going to minimize the low likelihood function over mu, tau, and hyperparameters. Okay. So now we're moving on to stimulation. So I have to consider, okay, based on this simple linear regression model, I'm going to consider cases, 3 different cases of sample sizes, 50, 200, and 500. And also for epsilon, for 4 different cases of error distribution, where the first one is normal distribution and the second is T distribution with 3 degrees of freedom, and the third is skew T distribution with gamma equals 4, where gamma is skewness parameter, and last is concatenate distribution, where it allows some outliers in this distribution depending on Q. I have 3 different values of Q here. And finally, I'm going to compare proposed method with a symmetric method like Huber and ordinary least square. And then for entire experiment, I'm going to repeat 100 Monte Carlo simulation, and then I average or error, average or estimators and obtain standard error. Okay, so I'm going to skip this. So I will show you the results. So now you can see if we have epsilon following normal distribution, you can see that symmetric method perform the best because obviously they work best in a symmetric case. But with the second case of epsilon, you can see for T distribution, both proposed method perform the best. Then the same for the third case, epsilon following skewed T distribution, they also perform better than symmetric case. Especially you can see symmetric method perform poorly because they don't take account of symmetry. And you can see values of tau estimator for first two cases or epsilon, you can see tau equals 0.5, which means they are median estimators, but the third case tau is somewhere close, 5th to 10 percentile. Okay, and one more for fourth case of epsilon. For different values of here for outliers, you can see in almost all cases, proposed method perform better than symmetric method, except Q equals 2.5, where the Huber method perform better, but otherwise, in most cases, proposed method perform better. And then finally, I'm going to apply proposed method to financial application on for stock market, US, UK, Australia, and Russia. Its data is extracted from Yahoo Finance, covering 12 years from 1st May 2010 to May 1st, 2022. And using this formula for daily percentage log return, log return zeros. Okay, when PT is adjusted price index for daily. Okay, yes. So I have given you a summary statistics of each stock market. I'm going to go over it very quickly. Skewness. Okay, so in summary statistic, I have a mean, skewness, quotients, and quantile levels, some extreme values up there. And so skewness is measure the shape of the distribution, and zero skewness indicates symmetry. Here we see I have all negative skewness values, which indicate their distribution is less skewed. And for quotients, it's measure shape of the distribution tail. So zero quotients means distribution is normal. As we can see, we have all positive quotients value, which indicate that they have heavy tail in their distribution. Okay, so I have obtained these results, but okay, based on these estimators, I can visualize what's happening. So I picked each histogram for each stock market, and I fitted density curve for Bayesian and maximum likelihood estimation method. So I have two curves. So they both fit very well to each distribution. So we can see these estimators are very good. Okay. Okay, so finally, I'm going to conclude. We can see that it's very important to develop a robust model to deal with non-symmetric problem. So, so in this case, I propose a new loss function where we derive a PDF and scale mixture of normal, and then based on scale mixture of normal, it's easier to develop Bayesian method, and also for frequency method, maximum likelihood function, estimation. Okay, so you can, as you can see, in stimulation and financial application, we saw that these proposed method can take account of asymmetry and habitable for distribution. So we can see that especially symmetry method perform poorly when error distribution is both asymmetry and habitable. And that's all. Thank you very much.
So thank you, Sanna. And we have time for a very, very short question. Is there some?
Thank you for your talk. I would like to ask if there is any difference in computational time between the two methods, the Bayesian and the maximum likelihood.
No, I wouldn't say much difference. They work really fast. I'm using R Studio and I don't find it too much. It would take long to. It would take about up to 1 minute to run 100 MC simulations for both methods.
Okay, thanks.
And sorry, just one curiosity. Why don't you use, for example, a gamma distribution that is asymmetric with habitables? Have you tried, or is it just a curiosity?
It depends on some application. So this asymmetric Nonconvex Huber distribution can be robust to outliers, and it's asymmetric, and it can take account of habitables. So asymmetric gamma distribution doesn't take account of habitables in this case.
Okay, thank you very much.